Okay, so welcome everyone. It is an enormous pleasure to have an really extraordinary speaker today, Tsu-Jae King Liu, and she's going to represent the Electron Devices Society. So during this 1 year, 25th anniversary for Women in Engineering, we had several presentations. And many of them, they were referring to, of course, robotics, data transmission, so very technical applications. And all of them, they were, of course, using transistors and integrated circuits. Well, this year, and actually this month, 75 years ago, the transistor was invented. And it would be even more a pleasure and a great honor to listen from one of the people who pioneered some of the latest innovations on integrated circuits, Professor Liu, on what is going on today. So she's going to tell us about sustaining the semiconductor revolutions, transistor scaling, and beyond. So I was supposed to say a few things about Professor Liu's career. She's a Stanford graduate. She's now a Berkeley faculty, member of prestigious societies and companies. She's an inventor and pluri-awardee. And I will just stop there because otherwise it would take me all the time of this seminar just to go through all these incredible achievements that Tsu-Jae King Liu has. So it is a great pleasure to have you, Tsu-Jae, as our extraordinary speaker on this seminar series today. And I would also like to thank Bozena, who is sharing the organization of that with me, all the staff at the Women in Engineering IEEE, who has been fantastic in helping through, Ramalata Marimutu and her team for all the publicity, and of course, all of you for being here today with us to share this really very, very great moment. So thank you all, and I will give you the floor, Tsu-Jae, for your presentation. Thank you.
Thank you very much, Dr. Devia, for that very kind introduction. And good morning or good evening, everyone. It's an honor for me to give this seminar as part of the Extraordinary Women, Extraordinary Science series, celebrating the 25th anniversary of IEEE Women Engineering. All right, so the proliferation of information and communication technology has had revolutionary impact on society. Now, we would not have been able to function as a society without the ability to stay connected while staying physically isolated amid the pandemic. Today, cloud computing, big data, and artificial intelligence are driving the digital transformation of all industries. Okay, let me see if I can advance my slide. Now, shown here in this slide is a vision of the future in the age of ambient intelligence. Advancements in information and communication technologies have given rise to cloud computing and the Internet of Things, which together with advancements in machine learning are giving rise to artificially intelligent systems for managing critical infrastructure for smart cities, for managing personalized healthcare and medicine for smart hospitals, automating vehicles and optimizing traffic flow for smart highways, and optimizing operations for smart factories. Artificially intelligent systems require real-time processing of large quantities of data. This is possible today because the capabilities of computing devices have improved dramatically over the past 120 years and are rapidly approaching the capability of the brain. Kurzweil's law states that the performance of the most advanced computing device, measured in the number of calculations per second per dollar, increases exponentially with time. And this is because the technological innovation itself is accelerated by advances in information technology. Underlying Kurzweil's law is Moore's law, which states that the number of transistors on the most advanced microprocessor chip doubles every 2 years. Today, the most advanced microprocessor chips comprise over 50 billion transistors that are powered and interconnected with a crisscross of wires formed from more than 12 layers of metal, patterned in this so-called back end of line process to achieve the desired chip functionality. Steady advancement in chip manufacturing technology over the past 50 years has enabled smaller transistors to be fabricated so that more of them can be interconnected together on a single die to provide for improved chip functionality and lower cost per function. This in turn has enabled new electronics products with greater information processing capability, resulting in market growth. Semiconductor companies continually invest a portion of their profits to advance technology to sustain this virtuous cycle. Now, the ordinary citizen is more interested in the impact of Moore's law. So in this slide, I showed that the number of devices, computing devices, has increased exponentially over time with the advancement of technology, allowing for greater levels of integration, so more functionality per device, and also increased cost effectiveness. And today we've seen the emergence of the Internet of Things. The industries with the greatest potential for the Internet of Things include utilities like smart metering and distribution, agriculture for crop yield improvement, healthcare, leveraging human capital in clinical trials, and autonomous driving for vehicles. Those are just some examples. Now, if you look at that previous slide, the number of computing devices is expected to reach hundreds of billions. And that's far more than the number of people in the world. So this means that there will be many more computing or interconnected computing devices than people. It's pretty amazing how rapidly, or how the electronics is proliferating. And a lot of that, the Internet of Things devices will be collecting data. So this slide shows over time how much data is generated by number of zettabytes. And we can see a few years ago, we actually transitioned to a data-centric world where most of the data that is generated is autonomously by electronic devices. So this is powering machine learning and artificial intelligence today. So if you look at how technology has advanced in the past, traditionally device engineers like myself, have focused on miniaturizing the transistors because this can provide for improved transistor performance and integrated circuit performance. And this translates to system performance. And over the years, the industry has developed technology roadmaps so that the equipment suppliers and the research community can be in sync to develop future technologies to ensure the continuance of Moore's law. So traditionally, like I said, we just focused in our layer of abstraction, and that we knew that if we improved transistor performance, we would end up with higher performing computing systems. So today, I'd like to talk about continued transistor scaling into the future, how that's going to be enabled by new structures and materials. And of course, eventually transistor scaling will slow down or stop. So we need to find solutions beyond transistor scaling. So I'm going to talk about some new switches and circuit architectures that would allow us to continually improve the computing performance in the coming years. And then finally, I'll conclude with some a summary. Okay, so in this slide, I show how MOSFET transistor scaling, the traditional metal oxide semiconductor field effect transistor, or MOSFET, has scaled in this century. So in the early 2000s, the most advanced technology was the 90 nanometer node. And this is these are cross-sectional transmission electron micrographs of transistors showing the gate electrode over the semiconductor substrate, and the source and drain regions of the transistor are electrically conductive, and the region in between them is the channel whose conductivity is controlled by the gate voltage. Now we can see as industry advanced the technology, slightly different materials were included. It's hard to tell here, but starting at the 90 nanometer node, Intel was the first to incorporate silicon germanium alloy in the source and drain regions to induce mechanical strain on the channel to enhance the effective mobility of electrons moving across the channel to enhance the on-state current for improved circuit performance. Starting at the 45 nanometer node, advanced materials in the gate electrode stack were introduced. So we have a high permittivity gate dielectric to provide for improved capacitive coupling between the gate and the semiconductor channel, to provide for improved oxide capacitance, gate oxide capacitance, and that provides more charge in the layer when the transistor is turned on. So this enhanced transistor performance. And you can see, and then we had metal gate because that's more compatible with the high permittivity gate dielectrics. One interesting thing to note is that the gate length, these are all on similar scales. So the distance between the source and drain regions, or the width of the gate electrode here, did not really scale through all those generations of technology. And the reason for that is because of the so-called short channel effect. This is a cartoon schematic of the metal oxide semiconductor transistor. So the capacitive coupling between the gate and the channel region is important for controlling the conductivity of the semiconductor between the source and drain regions. But as you make the gate length shorter, that is, make this electrode narrower, you're bringing the drain closer to the source. And so when the transistor is in the off state and you're trying to prevent current from flowing, but you have a high source drain voltage difference, the drain can help to turn on the transistor. So we see this in effect, a lowering of the threshold voltage. So the voltage needed that you need to apply to the gate to turn on the transistor actually is reduced, because the electric potential barrier between the source and the channel region is actually affected by the drain voltage when the drain comes too close to the source. And if you look at the current versus gate voltage characteristic, this translates to a higher off-state leakage current because of this threshold voltage reduction. So this is something that's not desirable, and that's why it was difficult to scale down the gate length. Now, ultimately, the off-state leakage current limits the energy efficiency of any complementary MOS digital computing circuit. And so if we look again at the on-off current ratio of a transistor, it's going to depend on the circuit supply voltage, VDD. So as we lower the supply voltage of a digital computing circuit, we don't have to charge and discharge the voltages as much. That saves energy. However, if we lower the supply voltage, that will reduce the on-state current of the transistor, and this will slow down the circuit. So the portions of the circuit that are static, that are just wasting power because of the transistor off-state leakage, are going to consume, well, because it takes longer to perform a function, you'll leak power for a longer time. So you spend more energy, static power and energy consumption. Now you can speed the circuit back up by designing the transistors to have lower threshold voltage, but this increases the off-state leakage current exponentially. So no matter what you do, as you lower the supply voltage, the amount of energy that's consumed due to just transistor leakage increases. And so if you total the amount of energy needed to perform any digital logic operation, there's a lower minimum that exists. And it's around between 0.2 and 0.3 volts today, just for your reference. So fundamentally, the energy efficiency of a CMOS circuit or CMOS technology is limited by the transistor off-state leakage. And so this is why the industry had to transition to a new transistor structure called the FinFET today. It's a so-called three-dimensional tri-gate transistor. Instead of having the gate controlling current flowing through a planar surface of silicon, we first patterned the silicon into a tall and narrow fin, and the width of that fin needs to be narrower than the gate length in order to adequately suppress the effect of the drain on the electric potential barrier. So that's the key to the FinFET. So if you look at the current versus voltage characteristic, it results in a steeper sub-threshold swing because of better gate control compared to the drain capacitive coupling. And so this allowed the industry not only to get better on-off current ratio for higher performing circuits, but it allowed the industry to scale down VDD, the supply voltage as well. So this is good for improving energy efficiency for computing. Now, in the late 1990s, and we first introduced the FinFET, and in the early 2000s, we showed that it was scalable to 10 nanometer gate length, as long as you make the fin width sufficiently narrow. So Intel was the first to put this new transistor design into high volume manufacturing in 2011. So I'd just like to point out that it takes at least 10 years for any innovation in a research lab to transition to high volume manufacturing. Now, a downside of the FinFET is that the width of the transistor now is the height, corresponds to the height of the fin, because this transistor is tilted on its, turned over on its edge. And so if a circuit designer would like to have a transistor, a FinFET, conduct more current, then it has to increase the effective channel width. And that is done by putting multiple fins in parallel to achieve higher ion. So this is an example where you have a 2-fin FinFET to double the current flow between the source and the drain regions. So it's interesting that today, in terms of technology advancement, energy efficiency is really becoming a driver of advancing technology. This is a chart taken from a talk by Mark Liu, who's the chairman of TSMC, the world's leading semiconductor foundry. This is a metric called EEP. It's the inverse of the product of the time per operation, so the delay. We would like that to be as small as possible for faster computational speed. But also this figure of merit includes energy per operation, so energy efficiency. We want energy per operation to also be minimized. So he charted this measure of this performance metric, and you can see it's actually improving exponentially over time, but that's enabled by these innovations that I talked about in materials, so high K metal gate, strained silicon technology, FinFET, and today extreme UV lithography, high mobility channel materials, and design technology co-optimization. So this is what's really driving a continued advancement in transistor technology. So looking back then through this century, we saw an evolution of the transistor from planar to a 3D or a thin body structure. And over several generations, we see that the shape of the fin has become narrower and taller. And this way you can have more current flowing per unit layout area. And just this year, Samsung Electronics announced that it was starting to produce chips with gate-all-around transistors. So this is the next step in the evolution, where we have the gate not only wrap around 3 sides, but all 4 sides for even better control of the channel potential compared to the drain potential. And this will allow for even further reduction in the gate length. Now, in order to have good layout area efficiency, if you wrap the gate all around and keep the body thin in all dimensions, you're not going to have much effective channel width. So you need to stack multiple channels on top of each other in order to have good layout area efficiency. And for even better efficiency, I like to make these nano wires, these silicon nanowires, even wider to provide for more current per unit area. So this is the leading edge transistor technology used in high volume manufacturing today. But you might imagine that the fabrication process is not very simple for a gate all around transistor. Now, in order to form this complex stack, we start with the silicon wafer, but we have to grow epitaxially layers of silicon germanium, and then silicon and silicon germanium, and so on. So you have to grow a stack of semiconductors, perfectly with epitaxially with no defects before you pattern the semiconductor into tall fins and continue the fabrication process. And eventually, later during the fabrication process, you selectively remove the silicon germanium layer. It's a sacrificial layer to form air gaps, and then you can form the gate dielectric and the gate material stacks to wrap all the way around these nanowires. So the manufacturing process is more complex, and therefore the cost actually is not actually going down per transistor. So this is a challenge, because now as we advance Moore's law, it's an economic law, but now because of the added process steps, it's not necessarily going to be cheaper per transistor to advance to follow Moore's law. So several years ago, my research group introduced an intermediary concept called the inserted oxide FinFET. So let's look at the schematic cross-section of a FinFET. It's a tall and narrow fin, and you have the gate dielectric, the high permittivity gate dielectric wrapping around it, and the metal gate. And then you have shallow trench isolation oxide on either side, just to isolate this transistor from neighboring devices. Now, with a gate all-around device, you need to insert the gate material and the gate dielectric in between each silicon channel region. And so in order to form this structure, you have to form a pretty high aspect ratio structure. And if you have fins that are closely packed together during the fabrication process, when you pattern them, they can actually end up tilting and touching each other. So it's not trivial to make fins with high aspect ratio, especially if you want to pack them closely together. So for that reason, we proposed, well, rather than putting the entire metal gate stack in between each silicon channel, why don't we just introduce only a simple oxide layer in between each channel region? So this way we can have a much shorter stack than the gate all-around FET requires. So it's easier to manufacture. And this oxide layer allows fringing electric fields from the gate electrode to penetrate in the channel region to help control the electric potential of the channel for improved gate control. So if we look at the iFinFET versus the nanosheet FET, we actually find that, so today the industry is going to move to, they know how to manufacture nanosheet or gate all around. But even then, if we actually avoid forming the entire gate stack between the channel layers, we can actually fit more channel regions in the same height of total silicon and silicon germanium that's etched. So I think that the iFinFET provides some improved layout area efficiency. And indeed, if you look at the current per footprint, comparing the nanosheet, nanosheet is just here. The ratio of the current for the iFinFET to nanosheet FET, it actually, the iFinFET is advantageous for small footprints. And this is important, especially for compact circuits like SRAM, memory cell arrays. So let's talk about the standard 6-transistor SRAM cell design. This is an eye chart, so I just wanted to illustrate the FinFET, the gate all-around FET. IMEC in Belgium proposed, or people in Europe proposed, a fork sheet FET to merge the N-channel and P-channel FETs. We compared that as well through simulation in the iFinFET. So for the most compact circuits on an integrated circuit chip today, the SRAM cells are most difficult to design and to scale the voltage down. So I just wanted to show this chart showing that the iFinFET SRAM cell actually ultimately provides for the best scalability in terms of voltage and performance in terms of read access time and write access time, because it has higher current per unit layout area, and it has lower intrinsic delay because you get higher current, but not as much increase in the gate capacitance, because the gate does not wrap all the way around. So I think the iFinFET can help to continue to advance transistor evolution. So we know that eventually, these gate all around or iFinFET devices will need to be stacked on top of each other, N-channel and P-channel stacked on top of each other to improve layout area efficiency. And maybe in the longer term, rather than silicon, we can introduce some alternative channel materials that are even thinner to allow more current per unit layout area, because you can fit more of these channel layers within a reasonable stack height. So I just want to mention that researchers at Berkeley already showed that these 2D materials, such as molybdenum disulfide, can actually be scaled down to 1 nanometer gate length. This is experimental. These are experimental results shown here for a molybdenum disulfide MOSFET that's shown here, that's gated by a carbon nanotube of diameter 1 nanometer. So it shows functional transistor performance. So we know that Moore's law will continue with transistor scaling for well past the end of this decade. But the cost is not necessarily going to be improved. And also, fundamentally, the subthreshold swing of a MOSFET cannot be steeper than 60 millivolts per decade at room temperature. So energy efficiency is going to be continually a challenge for CMOS. So this is why we should look at switches beyond simple transistors. So let me talk about this next. Now, years ago, when I was attending a talk at the International Electron Devices meeting, there was a talk by a vice president of NVIDIA, John Chen, and he was telling the audience, device technologists like myself, that really what device circuit designers want from device people are switches or transistors that have zero leakage, zero variability, and zero cost. Because of the fine variations in manufacturing of the gate length, you might have variations in the off-state leakage current, and that's not something that the circuit designers like to deal with. So, because the energy efficiency of a CMOS-based digital computing chip is fundamentally limited by off-state leakage current, my group started looking at mechanical switches. Now, you might have noticed in the chart on Kurzweil's law that electromechanical switches were used for digital computing back in the early 1900s. And so we're going back to revisit the past. But now, using state-of-the-art nanofabrication technology to make nanoscale electromechanical switches, it's worthwhile revisiting. So the benefit of a mechanical switch is that it has zero off-state leakage. And this is because there's an air gap between the source and drain electrodes and the off-state. Now, to turn on the switch, a voltage is applied to the gate electrode, which induces electrostatic force that actuates the movable conducting electrode into contact with the fixed conducting drain electrode. Now, the switch current increases abruptly when the gate voltage reaches the turn-on voltage. And the smaller this actuation gap is, the smaller the voltage that you need to apply to achieve the necessary electrostatic force. Now, to turn off the switch, the gate voltage is reduced so that the spring restoring force of the deformed electrode actuates it out of contact. Now, due to contact adhesive force, however, the turn-off voltage here, if you lower the voltage, it turns off. Turn-off voltage is smaller than the turn-on voltage, and this results in a hysteresis voltage VH. Now, through materials engineering, VH can be minimized to enable millivolt gate voltage swings. So my group has demonstrated circuits operating with VDD down to 25 millivolts. So that's about 10 times smaller than the minimum voltage for CMOS, where you achieve that minimum energy point. So this is 10 times, is that 10? Yeah, it's actually 100 times smaller than, it's 10 times smaller than for CMOS. So then this saves the dynamic power consumption, not to mention zero static power consumption. Now, this is achieved, such low hysteresis voltages are achieved through materials engineering. So that's pretty straightforward. Now, and I forgot to mention, even if you have variations, small variations in the turn-on voltage and turn-off voltage, as long as both of these voltages are greater than zero, you will always have zero off-state leakage. So that eliminates the problem of variable off-state leakage with varying turn-on voltages that is seen for transistors. So the final requirement is zero cost, and I take that to be zero incremental cost. So let's look at how technology has advanced over time. Not only have transistor structures and materials been evolving, but also the back end of line interconnect materials and technology have evolved. So the most modern integrated circuits today have have wiring with air gaps in between them. So it's not too hard to imagine that these metal electrodes with air gaps between them can be adapted to achieve integrated, 3D integrated on top of CMOS nano electromechanical switches. Okay, so design optimization of CMOS plus these movable nano electromechanical switches should leverage the advantages of NEM switches while avoiding their disadvantages. The disadvantage of a mechanical switch is that its switching speed is slower than that of a transistor. But compared to a non-volatile memory device, it is much faster. So a NEM switch can be designed to maintain contact with no applied voltage if we make the spring restoring force stronger than the movable electrodes, so weaker, than the contact adhesive force, so that it will stick once you remove the voltage. Furthermore, a NEM switch can be much more functional than a transistor. So shown here is an example of this single pole double throw switch design implemented using multiple back end of line interconnect layers and via layers to form a conductive movable electrode. The actuation electrodes on either side of the beam are formed from the lower interconnect layers, and they are used to electrostatically actuate the beam to the right or to the left into contact with data line electrodes in an upper interconnect layer. Now, the vertical orientation of this movable beam provides for a more compact footprint and is conducive to implementation in a cross-point array architecture. So the footprint of this reconfigurable interconnect is smaller than that of can be smaller than that of an SRAM cell. And finally, since the back end of line NEM switches are implemented in layers over CMOS devices, it's straightforward to integrate a diode in series with each movable electrode to prevent sneak leakage current in a cross-point array, which I will show in a subsequent slide. First, let me tell you how we fabricated these at UC Berkeley. This schematic cross-section illustrates the back end of line layers in a typical CMOS foundry process, which has been patterned to form the single pole double throw switch shown previously. The upper metal layers are patterned to form a hard mask for an etch process that is performed at UC Berkeley after we receive this chip back from the foundry. This etch process removes all the many layers of dielectric material, and this can be more than a micrometer thick, and the air gap here is approximately about 100 nanometers. So we use reactive ion etching with a inductively coupled plasma, and in between we use some wet etching to remove polymeric byproducts during the reactive ion etch process. All right, so here are some scanning electron micrograph images of the first multi-layer back end of line NEM switches, which were fabricated using a standard 65 nanometer generation CMOS process at Texas Instruments. Plan view scanning electron micrograph on the left shows the switch as fabricated before it is actuated. So the top of the movable beam is seen to be physically isolated from either of the data line electrodes on either side of it. The SEM image in the middle shows the switch after it's been actuated into contact with the D0 electrode. And the cross-sectional SEM on the right shows a cross-section with all of the electrodes labeled, so the actuation electrodes on either side of the movable beam in the lower layers, and then the conductive data line electrodes in the upper layer, electrically insulated by the interlayer dielectric. So this is these are experimental results, and let me show you some measured electrical results. So the programming voltage, the voltage needed to actuate the beam back and forth is still rather large because the air gap is 100 nanometers. But it matches what we predict from experimental simulation. 65 nanometer node, and also later on we used TSMC's standard 16 nanometer node to fabricate even smaller switches. And as the air gap gets smaller, then the actuation voltage goes down. So we can project that as we use more advanced technologies with smaller and smaller pitch, in other words, smaller and smaller air gaps, the switching voltage of these NEMS devices can become compatible with CMOS transistors, so approaching 1 volt, just to change the state of this reconfigurable interconnect. Okay, so how do we, at Berkeley, we're exploring new hardware architectures for edge computing devices for which energy efficiency is a critical requirement. So shown here are experimental results for a hybrid CMOS. On the bottom, you can see these FinFETs and NEMs. These are patterned beams in the back end of line interconnect so that they can move back and forth. This is a circuit implemented using TSMC's standard 16 nanometer CMOS process. And this cross-sectional SEM shows the fabricated circuit on the left, and shown in the middle is a circuit diagram. Now, this is a diagram of 4 rows of each comprising 2 of those NEM switches, and each switch is pre-programmed, using the actuation electrodes, so that each output bit line, these horizontal bit lines, will be driven low only when the input string, which is input here vertically, matches the stored data for that bit line. So for example, if the input string is 0, 1, as shown here, then only this line, which stores 0, 1, will be pulled low. And so what we did was we cycled the input bit lines through all the possible 4 combinations, input A and B, and we see that it's pulled low only, this line here, the 3rd line here, is pulled low only when the input string is 0, 1, which corresponds to the stored data in that row. You might notice that the high voltage, the output line is actually degraded because of the diode that's built in to prevent sneak leakage current through this cross-point array, but we can easily restore the high voltage level to full VDD using CMOS buffers that are integrated underneath NEM switch array. So this function is essentially a data search operation. This decoder, decoding a 2-bit string into a single line, 2 to 1 decoder, is essentially perform a data search. You input a string and you find out like which row that string is located in. Now we can enhance or augment that previous circuit, which pulls down 1 output bit depending on the stored information, and implement a lookup table. Okay, so the way this lookup table works is as follows. Well, first of all, why are we interested in this? Well, for Internet of Things applications, it's sometimes more energy efficient to look up an answer in stored memory rather than to calculate the answer. So a lookup table has potentially a lot of applications for Internet of Things applications. So by simply adding 1 or more columns of back-end of line NEM switches and complementary pairs of output data lines to the decoder circuit shown before, and using gated CMOS buffers to allow the output data lines to be electrically isolated from the input data lines so that they can be pre-charged high while the input data lines are being driven, we can achieve a compact lookup table. So the output bit line, remember, is pulled low only when the input string matches the data that's stored. And using a gated CMOS buffer, then we can translate that or transmit that low voltage to the output bit line portion of this array. And depending on the switch that's programmed in the output portion, you can discharge one of the pairs of output bit lines to read out the information stored. Now, over time, of course, you can reprogram these switches to change state. So this is a reprogrammable lookup table. And so in this particular example, we stored in the output just 1, 0, 1, 0 alternating states. And so as we cycle through all the 4 possible combinations of input addresses, you can see the output bit line voltage cycles up and down to 1, 0, 1, 0. So this is a demonstration of a CMOS plus NEMS lookup table. And if we want to benchmark the performance of this compared with a pure CMOS implementation, which requires an SRAM cell, but then the data, the information you're looking up needs to be loaded onto the SRAM cell from non-volatile storage before you can input the address and then read out the answer. Whereas the NEMS CMOS plus NEMS implementation is much more compact. So with regard to area, it's the CMOS plus NEMS implementation is orders of magnitude more efficient. So this radar chart, the larger the area, the better. We compare the CMOS plus NEMS implementation against the pure CMOS implementation. And interestingly, in terms of the readout delay and the readout energy, it's also orders of magnitude better than the CMOS implementation. So this is just an example of how you can cleverly use the NEMS technology together with CMOS to achieve energy efficiency and performance that's exponentially better than pure CMOS to sustain Moore's law. Finally, my final example is to look at completely different computing architectures. So rather than representing ones and zeros in a computer by high and low voltage, we could implement oscillators that are binarized with binarized phases. So in phase or out of phase is 0 degrees or 180 degrees phase. And we can achieve these two, we can binarize phases of oscillators by using a process called subharmonic injection locking. So you can sort of inject into each or disturb each oscillator with a signal that is roughly twice the natural frequency of that oscillator. And the oscillation will naturally lock into this subharmonic injection locking signal, signal, in one of two phases, either 0 degrees or 180 degrees. Now, why is this interesting? Well, it's interesting because now you have this binary state, and then you have oscillators that can be coupled electrically to each other in a network. Okay, and this is a so-called icing machine, and these have been shown to be potentially very advantageous for solving combinatorial optimization problems, which are very common for our artificial intelligence applications. So an icing machine comprises a network of discrete variables that can have one of two states, and they call them spins, up or down. So each spin takes a binary value, and depending on how they're all coupled together, they eventually will settle into a state that minimizes the energy of the system. And so you can map a combinatorial optimization problem onto an icing machine by assigning appropriate values to these coefficients J, which correspond to the coupling strength between spins. So this is the icing Hamiltonian, and you can leverage physics, which naturally wants to minimize the energy of any system, to automatically solve a combinatorial optimization problem. Okay, so in an oscillator-based icing machine, the phase of each variable oscillator takes a binary value of 0 or 180 degrees through subharmonic injection locking to minimize the overall energy consumption of the system. Okay. All right, so why do we care? This is an example that's relevant to our field. For example, if we want to minimize the layout area of a chip to save cost and improve manufacturing yield, that's related. Usually a chip has multiple blocks of circuitry, and you want to floor plan to minimize the total area of the chip that comprises all these blocks. So this problem can be formulated as the rectangle packing problem, which is an NP-hard problem. So given the problem is defined as this, given n rectangles with fixed sizes, as shown on the left, the goal is to minimize the boundary box area, which is W times H, without overlapping of the rectangles. Now, a brute force search can be used to solve this problem, but it requires large computational resources and time, especially when n, the number of boxes or rectangles, becomes very large. Instead, this problem can be mapped onto an icing machine with 3 times n to the 3rd power spins and solved within several oscillation cycles for much faster time and lower energy to reach the solution. Now, the reason I'm mentioning this, I forgot to mention, is because mechanical beams can easily be made to resonate, and so you can have an oscillatory signal formed. Now, the experimental results I'm showing you here were achieved with a micron scale mechanical switches, not the nanoscale switches I've shown earlier, because we just want to do proof of concept. So these micro scale electrical switches, micro electromechanical switches, have 4 electrodes. They have the source and drain conductive electrodes, they have the gate electrode, but they also have a reference body electrode. So we injected a subharmonic injection locking signal that's roughly twice the oscillating frequency of these MEM switches, which is about a megahertz. We injected that into the body electrode, and then we turned on the gate electrodes to turn on the oscillators. So the 2 different colors here, blue and gold, the drain voltage signals correspond to the two different relays that were turned on at different times. So you can see that within about 10 oscillations, the oscillation phases are locked into phase. And the reason for this is because the relays are coupled together in parallel. So the drains are tied together through a coupling resistor, and sources are tied together through through a resistor as well. And in order to minimize energy consumption, we want to have zero voltage difference between the drains and between the sources, so that no current flows in those coupling resistors. And that's why these relays ended up oscillating perfectly in sync with each other. So this is just an experimental demonstration that mechanical switches can be made to oscillate and can be used to implement coupled oscillators. So this is promising for implementation of icing machines. So just to conclude then, I hope you see from the examples that I've shown here today that the system level perspective rather than the device level perspective can influence device innovation. If you were only focusing on device innovation, you would never think about going back to a mechanical switch, because a mechanical switch is larger in footprint and it's slower in turning on and off compared to a transistor. But if you have a system level perspective, then it turns out to be worthwhile to consider these switches because they have zero leakage and some other interesting properties. So by having a system level perspective and co-designing the circuit and the system with the device, you can achieve dramatic improvements in computational speed and energy efficiency for specific applications. So I think there's much room for innovation in materials, devices, and chip architectures to sustain this virtuous cycle of technology advancement. Rather than transistor scaling, it's going to be driven by co-design and innovation across all those technology layer stacks. So looking forward in the future, there will be different dimensions of integrated circuit technology advancement. Of course, new devices and materials, new chip architectures and packaging, new computing paradigms. And we need to co-design and innovate up in this three-dimensional design space to achieve exponential improvement in computing power. So that's kind of the conclusion here, is that in order to sustain Kurzweil's law, we need to have applications drive innovation in materials, devices, and architectures in the future. Now, I'd just like to end with some acknowledgements. This work wouldn't have been possible without the hard work of many people. So I'd like to first acknowledge the many talented and motivated graduate students and postdocs with whom I've worked. These students, Fei, Dennis, and Peng, were instrumental in looking at the FinFET, developing the FinFET technology, and the MEMS technology. The oscillator was developed by Shao Hu, and then those back-end-of-line MEMS devices were really just as a tour de force by Ermita Schichter. And the whole concept of CMOS plus MEMS was initially proposed by a visiting postdoc in my group, Kimihiko Kato. And I've had wonderful faculty collaborators at Berkeley and in Taiwan, National Cheng Kung University on the FinFET particularly, and lots of collaborators in industry, experts in technology, in device physics and technology computer-aided design, and people who helped get the back-end-of-line MEMS working first at Texas Instruments and subsequently at TSMC. And so I'd like to acknowledge all of the resources that were used for the back-end-of-line MEMS work. And of course, it wouldn't be possible without funding. But I'd like to also end by acknowledging people who've had extraordinary impact on my own career path. So when I was a graduate student, my husband, he was not my husband at the time, but he was a graduate student a few years ahead of me, really encouraged me to pursue the PhD, would not have earned my PhD without his support and encouragement through many years. Professor Krishna Saraswat was my thesis advisor. He was super patient, took many years for me to find a project that turned out to be promising. And then also Professor Plummer was a thesis co-advisor. And then when I was interviewing for jobs, Jeff Boker offered me a position at Bell Labs, which I eventually turned down, but you'll see why he's had a tremendous impact on me. My first job after graduation, permanent job, was at Xerox, the Palo Alto Research Center, and Dr. Ann Chang was my first manager, and she's been a tremendous role model for me. While I was there, I was able to collaborate with students, doing research at UC Berkeley and at MIT under the supervision of Professor Nathan Chung and Professor Raphael Reif. So Professor Reif ended up writing a recommendation letter for me when I applied for a faculty position at UC Berkeley. And at that time, Jeff Boker had moved over to the faculty at UC Berkeley. So he was there, and he was certainly one of my advocates and mentors when I was there. Of course, Professor Chen-Ming Hu is a great mentor to me throughout my time as a faculty member. And of course, both Chen-Ming and Jeff are co-inventors of the FinFET. Professor Roger Howe was at Berkeley at the time, and he we collaborated together on MEMS. So that's how I ended up doing research in MEMS. And also Shankar Sastry was dean, and he was the one who gave me the opportunity to step up into various leadership roles as department chair, and served as a good role model for me to serve as dean today. And for a few years, my husband, David, and I had a startup company, and was acquired by Synopsys. Just want to acknowledge people there, really helped to make that possible. And today we have a good collaboration with Synopsys, which does provide the TCAD tools that really enable us to explore new devices before having to fabricate them in the lab. So I just like to, I've always considered myself to be an ordinary person who's been extraordinarily blessed. I just want to acknowledge all of those people that I've been blessed to be able to work with. And also, lastly, I'd like to thank you all for your kind attention, and look forward to your questions. Thank you.
Thank you very much. It was really an inspiring presentation, Tsu-Jae. And I can see there are several questions on the chat.
Okay.
Modena, would you like to handle the questions?
Oh, sure. Thank you so much. It's extremely inspirational. I have always questioned, because I relate research with education. My question, when you acknowledge your graduate students, my question to you is, what kind of background you expect students whom you will accept to your group have? What kind of background? Do they have to be engineers, or they can be, I am a mathematician who does applications to engineering. So I'm curious. I'm just curious.
Well, I'm primarily experimentalist. So yes, all of my students, looking back, and postdocs are engineering. Well, actually, there was an exception. I took a graduate student who was majoring in architecture, okay, and he wanted to switch over to semiconductor devices and technology. So there are always exceptions to the rule, and certainly I've had students whose background undergrad was in physics or some other STEM field. So generally, STEM field, and just interest and motivation. My own thesis advisor was very patient with me, and I've always tried to remember that and be very patient with my own students. So looking back, at Berkeley, we have a nice system where students can change advisors if they try out some research and it turns out it's not a good fit for them. So many of my students came from other groups. They started doing research in another group and found it didn't work out, and so I welcomed them. I pretty much welcome anybody who wants to work in my group, as long as they're motivated, and always interested to learn new things and to learn, especially from failures, right? Trying things and learning why they don't work. I think that's all that's needed. So a good, maybe technical background and interest, motivation to learn.
Did you develop some courses that you teach for at that graduate level, or maybe even undergraduate level?
Well, I did, and when I was working at Xerox PARC, I worked in the flat panel display industry. And so I did teach us a graduate level course on flat panel displays. This was back when displays like what we are all using were not really affordable. We were all still using primarily the cathode ray tubes. So that was quite interesting. We looked at, different types of flat panel display technologies, including liquid crystal, but also organic light emitting diode displays, which are prevalent today. At the undergraduate level, what I've done most recently as dean is to develop a new course co-taught with a professional journalist. It's the art of STEM communication, because I think engineers, we need to do a better job. We need to train engineers to do a better job of communicating effectively to people that are not engineers, right? So some of the work I've been involved in the past year or so, talking with people in Congress and in the federal government and so on. If you can't communicate the impact, importance of what you do to people who are not engineers, you're not going to be as successful. Let's put it this way. And so some of the work I've done has led to some extra funding for workforce development as part of the CHIPS and Science Act that was passed in the US just earlier this year.
Absolutely excellent. That communication. So one of my 5 favorite C's, I have those 5, I call C to the power 5, curiosity, creativity, connections, as you can see in your research, communication, and collaboration. So I just love that. Anyway, I would have 1,000 questions as always, but I would like to open to other people. You have so beautifully gratitude for and thanks for your absolutely inspirational and interesting and great inspiration and informative presentation. But here is a question. I got a question. Maybe you can open to your camera and ask directly question. This is from Moaz.
Okay.
Is it okay? Do you have a functioning camera? Oh.
Menzi, is that right?
Yeah. Hi, Professor Boo. Yeah, thanks for the great talk. I had a question on the slide 14. Mentioned the minimum total energy. The transistor. So just kind of like I put that as well.
I'm sorry, your audio is breaking up, so I can't actually understand.
So the question is in terms of scalability.
Scalability.
Can AEMS transistors compete with that CMOS?
You talk about scalability of the mechanical switches?
No, I'm sorry about the audio, but my question was on the minimum total energy that you mentioned about 250 millivolts.
Yeah, for CMOS.
Is that independent of technology nodes, or is it more restricted by the Boltzmann?
Right. Yes. So the minimum energy, the energy efficiency limit for CMOS. Yeah, it doesn't matter what the gate length is or the transistor structure. If it's a MOSFET, where you're changing the potential barrier height with the gate voltage, the steepest you can turn on and off is 60 millivolts per decade. So if you want a high on-off current ratio, you need some minimum gate voltage to achieve high on-off ratio. But yeah, I think that this subthreshold swing is ultimately limiting the energy efficiency of CMOS, and that doesn't matter what the transistor structure is or the channel material, actually. But you might all know that at Berkeley we have Professor Saif Salahuddin, who's been advancing the technology for negative capacitance transistors, which potentially can leverage the ferroelectric effect to achieve steeper than 60 millivolts per decade switching. But maybe that can improve it in the best case to about 30 millivolts per decade. So let's say you need an on-off ratio for Internet of Things applications, at least 10 to the 6. Okay, so 6 times 30 millivolts, that's still a couple of tenths of a volt. What I showed with the mechanical switches, and we've shown MEM relay circuits operating with 25 millivolts. So it's 10 times smaller operating voltage. So if you really want to get to millivolt logic, then you have to go to something other than CMOS, unless you're willing to go to cryogenic temperatures, right? lower temperature. So that subthreshold swing is proportional to temperature. So if you lower the temperature, you can get steeper swing. But then you just have to make sure that the energy needed to cool your CMOS, chips is not going to overwhelm the energy savings So you can get like 10 millivolts per decade subthreshold swing with CMOS if you operate at cryogenic temperatures. And the reason why it's not steeper is because there are always some defects at the semiconductor oxide interface that ultimately limit the steepness in which you can turn on and off a transistor. So it's never going to be better than about 10 millivolts per decade. So again, mechanical switches can outperform CMOS even at cryogenic temperatures, if that's what you really care about, energy efficiency.
Thank you, that helps.
We have a question from Stephanie Butler. Stephanie, would you like to ask directly question?
I can ask it directly, but not with my video. Don't want to break up my audience. So this is Stephanie Watts-Butler, formerly of Texas Instruments. So I met Professor Liu way back in the day when she was doing the great work with CMOS in the early days of high K, metal gate, and stress. So I wanted to give you kudos. I thought it was a really great review of the reasons for each development. I really think it's important for students to understand you were going through these technologies not because they were cool, but there was a reason that each one was developed. And you did it in a manner that I think the students could really learn from today. And you also talked about manufacturing variability and how horrible that is. But you didn't spend a lot of time talking about over-temp behavior, and especially when you look at some of these MEMS technologies or when you're combining MEMS with CMOS, and those two may have different over-temp behavior. Can you spend a little time talking about over-temp behavior? Because that's very important. And while manufacturing variability can also cause variability in the over-temp behavior, in and of itself generally is inherent to the technology. So again, kudos for the talk, and I look forward to your answers.
Thanks, Stephanie. It's great to see you here virtually. Great question. So indeed, the current versus voltage characteristics of a CMOS of a MOS transistor are sensitive to temperature, right? So the subthreshold swing changes with temperature. The threshold voltage itself also changes with temperature. Actually, generally goes down with temperature. So as you operate the chip, there's joule heating, and so you heat it up, and it affects therefore directly the performance of those circuits. The nice thing about mechanical switches, and that's why the circuit designers with whom I've collaborated really like them, is because they're ideal. Zero off-state leakage and good on-state conduction. And we've tested these microscale switches over a wide range of temperatures, from 4 Kelvin up to 200 degrees Celsius, because that's kind of the range of our equipment capability. And they all work just fine. In fact, mechanical switches operate better at cryogenic temperatures because we used tungsten as the electrode material originally. Of course, in the back end of line, those are copper. But originally we used tungsten because we were worried about physical wear, and tungsten is a refractory material. But tungsten oxidizes. So over time, the oxide forms, and then you get poor contact resistance, and then the circuit doesn't work eventually. But at temperatures below 90 Kelvin, oxygen is no longer a gas. It actually is a solid. So you don't have the oxidation problem. So mechanical switches actually are very robust to irradiation. There's no built-in electric fields, PN junctions to accidentally cause the nodes to be charged up under high energy particle irradiation. They work over a wide range of temperatures. So as long as you adjust the operating voltage to make sure you can always turn on the device and turn off, yes, there will be variations in the turn on voltage, but as long as you set the zero and VDD properly, it will always have good on-state conductance and always be off, like zero off-state leakage. So I think that's why I started looking at mechanical switches, even though they're larger and slower than transistors. But the circuit and system designers are looking for a solution that is zero leakage and zero variability in leakage current.
Yeah, Chincha.
Oh, sorry, I'm chipping in because it continues what you are saying, Tsu-Jae. Are you saying that also from the mechanical point of view, they are very stable? So independently of many switches that you are having, And as a consequence of that, also they are less prone to single event upset?
Oh yeah, definitely. They're not prone to single event upset. The most frequent question I get is about the endurance, right? How long can these mechanical devices last? Well, we know from simulation and from theory, mechanical engineers know how to design structures to last, because you just design them so that the maximum strain that the material has to endure is much, like 10 times smaller than the yield strain. And the examples I showed with the reconfigurable interconnects, the thing that wears out a switch is hot switching. So if you try to open it, especially, or close it when you're applying a voltage difference between those electrodes, that actually causes atomic movement from one electrode to the other. But the way we're using it in the circuit is we actuate it into contact or not without any voltage in the conducting electrodes. When we only flow current and apply a voltage difference and flow current when they're already touching. We never have a do hot switching where we're applying a voltage and moving them in and out of contact. So I think the endurance should not be an issue for cold switched back end of line NEM switches.
And they are not prone also to vibrations, so resonances of any kind.
Yeah, actually, I always have this question, so I have the slide prepared. Let me just share my screen one last time. So the questions about, shock, mechanical shock and so on. So the nice thing is these devices have very small mass. So you need a lot of G's to get them to move accidentally to turn on or off, that unintendedly. So a million G's is kind of more than a million G's is what you need to actually accidentally move these little beams. And a thermal vibration is, the gaps are nowhere close to an angstrom nowadays. So it's essentially, not an issue. I think like if let's say you want to put some electronics on a bullet, a projectile, and shoot it out of a gun, let's say that's probably like one of the most shocking applications. That's still less than a million G's, just for your reference.
Wow, thank you.
Anyway, I don't see any other questions. Maybe still somebody has question? Do we have question? One more time.
And to you're on mute.
Yeah, maybe one last question.
Thank you. Thank you for excellent talk and nice meeting you during MET conference with my daughter. And I have three short questions. First is, how many silicon nanosheet do you think we can stack? And second is, sorry. Okay. The second question is, for the FinFET, your two sidewall 110 has a high hole mobility. If you break it down as a nanosheet, so you are not taking the advantage of that hole mobility from the 110 sidewall.
That's right.
My third question is, if you have a 1 nanometer MOS2, but if I see their VDS, the VDS is 3 volt. How can I make a device descend on current for less than 1 volt VDS? Low voltage MOS device.
Oh, yeah, right. Yes. So that's the whole idea. Let me share this great question. Nice technical question. What I've seen, I've seen in a state-of-the-art manufacturing facility, 5 nanosheets, or these so-called nanoribbons stacked on top of each other. So I think that's not out of the question for NMOS and PMOS. And you do need to stack them in order to have a good amount of current per unit layout area. So the industry will continue to lower the voltage towards half a volt. And so you do need, that's why you need to stack so many on top of each other so that you have reasonable current per unit layout area operating at those low voltages. Yeah. So that's why, they're looking at, well, it's too hard to fabricate too tall of an aspect ratio structure. That's why they're thinking potentially going to 2-dimensional, very thin, skinny layers of channels. But there are definitely technological challenges to achieve these, even 5 nanosheet transistors uniformly and in high volume production. That's one of the reasons I proposed the FinFET, because you might know circuit designers, they want to have a choice of different flavors of transistors, low voltage, low threshold voltage for high performance, because that gives high on current, or high threshold voltage for low leakage power. So for low power circuits, they want to have a choice of multiple threshold voltages on a chip. And you can imagine with the gate all around structure, if you have different materials inserted into different transistors on a circuit, and today they want, I think, 4 different threshold voltages for both the N channel and P channel devices. It's so difficult to control the gate material in between those the nano wires or the nano sheets. The FinFET circumvents that problem because you don't have to wrap the gate electrode around all of the nanowires, just partially, right, to allow fringing electric fields. So I think there's still a lot of challenges to the cost-effective manufacturing of the gate all around or nanosheet, nanoribbon transistors. Maybe the FinFET will be used even to help improve the manufacturing yield.
Thank you so much.
Thank you for the good questions.
Thank you so much, and thank you to those who asked questions. And I don't see any other questions, so I believe it's time for us to let me be sure that there is nobody. Yeah, everyone, thank you, thank you. Thanks.
Right. Thank you so much for your kind attention.
So many, thank you. So Tsu-Jae, it's time to close the conference. Thank you so much to everyone and to you particularly for this outstanding, extraordinary talk. Thank you.
Well, thank you all.
Thank you. And so let me also join in in thanking you, Tsu-Jae. And please, everyone, join us for the last seminar of the series next week. So we have been looking at really at the very, very small, how to get really to the smallest of the small in our transistors. And next year we will be on the outer space of Mars, the pursuit of finding life on Mars with Dr. Mariko Sophie Bourgean and from the Geoscience and Remote Sensing Society. So thank you very much, everyone. Thank you very much to Seiju, lead you.
Thank you. Thanks to everyone, and all the best for you in continuing research. Thank you.
Thank you so much.
Thank you.
Thank you,
Everyone.
We had terrific audience.